This is one of the projects Hiroshi mentioned during his presentation. I decided to show you because it is deeply rooted in computer vision, but significantly different from what you potentially already seen in the internet. And this is about computer vision and 3D things. You can see a couple of images. The first one is an output that is created by special scanning machine that sees the structure of mouth. It's like kind of close to MRT, but not exactly. So the machine builds a 3D model of teeth and gum inside your mouth, and the output of this equipment is just a 3D model without any additional information. So all the points are heterogeneous, and human eye allows us to understand where the tooth and where the gum. But for software, initially it doesn't have any difference there. But what you see below is a picture that finally is going to be an output of AI system, one of the outputs. And what the system does is running segmentation procedure on top 3D data, and logically splits gum and each tooth separately, so that you get this scanned version of mouth, and then you get after AI has processed the input, you know the exact position of each tooth, and this is an input for further processing. For example, like recommendations about how you can move your teeth using different teeth plastic things, and it's actually a recommendation and visualization system for Japanese dentist project, so that dentist can take this 3D representation of your mouth using the special equipment, and as a result, you can get on the screen all the information about potential misposition of any tooth, maybe missing tooth, and some recommendations, some recommendations on how you can be treated with that. It's a treatment modeling tool, and also like something that helps doctors to understand what to do, and to explain people what they are going to do with their teeth. I consider this to be pretty interesting, and a couple of notes about that, why it is still computer vision. There is no optical input here, but what we get here is almost the same thing, but of alternative dimensionality. This is not 2D image, it is 3D instead. And in real life, for 3D objects, we still can apply most of computer vision techniques. And even some details I want to show you about that, how 3D data can be processed using computer vision algorithms. So as you remember, picture is a set of pixels. For 3D world, we have two options how we represent 3D objects. Originally, historically backgrounded, we have following type of representation of 3D models in any software, whether it is kind of design software Maya or something similar, or engineering software like CAD systems. So in 3D world, we have 3 axes instead of 2. And historically, each object could be represented there as a set of verticals that are connected to each other with some edges, so that we have polygons here, and each surface we can represent here is a set of verticals connected between each others. 3D object can be represented as a set of surfaces, or even some 3D areas can be completely filled with verticals with some density, and also for each vertical there is also meta info available with which other verticals we have these connections. So we operate edges, polygons, and verticals. This is classic approach. This is used in all software, in many games and movie rendering. And even with this material, we can already work using machine learning. For example, what is involved here is following thing. We have some verticals that logically are part of gum, and we have others that are actually tooth. And initially, the system knows nothing about. I will put this like some kind of line. It's virtual. To show that we can split points that relates to are related to gum from points that are related to tooth, and in fact we perform the segmentation task for 3D objects. This is how it could be done, but in modern 3D world there is another approach that seems to be the future of 3D modeling and 3D computer vision. And it is like more about logical movement from 2D world to 3D, so that we split all the space we have, 3D space, we split into 3D pixels. Let's say that any object there can be represented like this. So here we have 2-dimensional grid, but here already we could have 3-dimensional grid. And each small cube here let's say this one. Is the smallest particle of available resolution. Its size is very important and should be as small as possible so that we can represent any 3D object by using this 3D type pixels. They officially are called voxels. There is such a word. Like, so you can consider this to be 3D type of pixel. Yes, and yeah, I heard the question or not?
No.
So as you understand, this is almost the same thing. Here we have pixel in 2D world. Here we have voxel that is actually pixel in 3D world.
Volume pixel.
Sorry?
A volume pixel.
Yeah, maybe. Yeah. So it is a voxel. Yeah, and so we have the size of this voxel, its coordinates in 3D system, and also each voxel can contain some additional meta information. For example, value, for example, or maybe it can contain information about its class or color or material or anything else we need for our solution. And inside of this space, we can define some voxels to be like a empty space, other voxels to be a part of teeth, different ones, and others to be a part of gun. If we have initial model, just a binary split system like into voxels which are empty spaces and not empty spaces, we can feed this input about non-empty voxels. And on top of patterns and geometry structures we have for non-empty voxels, we can run segmentation predictive model on top of this space and understand which voxel belongs to tooth and which one belongs to gum. So that we can reuse all the set of convolutional neural networks in two-dimensional space to three-dimensional space. Of course, our convolution becomes 3D based. We used to have 3x3 convolutions here. Here we have like some cubes, convolutional cubes. We can still apply this thing to 3D or even higher dimensionality spaces and use this in 3D space. Actually, during the natural language processing course that is going to be maybe on 24th of April, something like this, we will also see how convolutional neural networks can be applied for natural language processing and signal processing with other dimensionalities of spaces. Now, so this is all actually still computer vision, but not optical computer vision. And this type of approach is widely used in medicine and in engineering and in many like scientific uh, fun things, including astronomy and so on. Learning the property of solid objects currently um, performed using like this type of modeling voxels, and all the 3D object can be split in many primitive small voxels. Having smaller size allows us to get higher resolution, and that's it. This is the same like for image. Yes. So this is what I wanted to say. Actually, what is your impression about Hiroshi speech? For me is a little bit more business oriented that like I expected from him a little bit more about project themselves, like some more details. But fortunately, I know many things about those projects, so you can ask questions because I'm familiar with all the activities he mentioned. But also interesting thing that he works with other implementers, other companies here in Kiev who implement things for uh, Japanese market in AI. And there are several interesting projects like photos and enhancements, automatic photo enhancing systems, mood detection systems like this. So he's quite involved in this AI industry. I really hope that it was interesting for you. Uh, and for me, it's like entering Japanese market was what wasn't easy thing to do for me because they are really closed economy. Like entering U.S. or Canadian or even Norwegian business, much more simple thing for me because all these countries speak English very well and they are Western-like cultures. But in Japan, becomes available for AILabs.org just because of having this business contact. So yeah, at least for me, this was interesting conversation with him. I hope it is so for you.
Yeah, thank you.
Actually, he's very like public and open. You can reach him and ask questions whenever you want to be surprised or something. Just if you want to know something about this more, you can ask questions. Okay, let's continue with our topic.
Sorry, Alexander, do you use Jabra?
Let me check. Maybe not, if you're asking. It says yes. So
Yes.
let me put speaker closer to me. Maybe because I turn my head to whiteboard sometimes, maybe it becomes less
Okay.
visible. Is it nice now?
I think it's better.
Well, actually, do you see the board well?
Yeah, not bad.
Yep.
Just a moment. Okay. So let's continue with evaluation and validation. So let's suppose we have already pre-processed our data, we have annotated our data, and we already have some data for training. You can have them as normalized images, or maybe as MBAI21 or any other format. These files can be stored on your research machine or in a cloud, and you potentially can so like almost among these three types will be your option. And for sure, for further research and development, you should split this data properly. The first thing you can do about this is to take entire data set, split in three parts: training set, evaluation, and test set. And this seems to be nice, but there are several problems with this splitting. And I want several guesses from you guys. What potential problems can we face here if we split data this way? I need just guesses.
So if we split the data between training,
Yes. Yeah. So we have many annotated data. We have data set. We want to develop something, and we know that we need something for evaluation to check the performance of system during the training, and test set to be able to report about final quality about our system. But in fact, here we have several potential issues we can face. So what's your guess about it? What's the problem?
Oh, some kind of bias in the data sets, not a good split, an even split.
Good point. And what weakness of this split could we face potentially? Okay.
It could, but potentially is that during the validation we get very good accuracy, yeah, but in real life we will get not good results.
So the answer is one of the answers is very simple. What if our dog cats data set is sorted one, and we take 10% for validation, 10% for testing, and other data for training. In doing this way, we get data set where for testing and for evaluation, we got just dogs, for example, and that's it. So first of all, many times I noticed that in real projects, people just forget to randomize the order. No shuffle of data. But this is not the only problem. Even if you shuffle your data perfectly, you still have not enormous data set usually. You have kind of maybe 1,000, maybe 10,000, maybe 20,000 examples, but sometimes it is even 500. And if you split data in 10, 10, 80, you still have quite high risk that this 10% slice of data won't be representative enough for entire thing. Its distribution can be different just because of randomness, just because of some unfortunate thing that happened during this split. For example, if we have 500 examples, we split 10%, it's 50. And among this 50, we potentially maybe don't have any cat of black color. Just random situation. But for other items, we have several black cats there, and our evaluation process further won't be checking the system for its ability to recognize black cats, right? Our evaluation won't show anything about it. So this is a couple of problems. Also, we
Could
should
be also,
yeah.
it could be also the problem of the background, yeah. This is also famous case, yeah, when there was some weapon system, yeah, for tank determination, yeah, object, but in fact, it finally figured out that it didn't analyze the tanks, but analyze the sky, yeah, because all the pictures were like tanks and background was sky, yeah. And when there was night, yeah, or something like this, that actually system didn't recognize.
Actually, yes. Having fewer examples reduces our diversity of options of background there, and this can makes us just not able to measure the quality of certain types of backgrounds or detection certain types of backgrounds or anything. So yeah, especially problem becomes more significant if we have not balanced data. Let's say we have 5,000 examples, but and we have two classes there, but not 50-50% representation, but instead we have, let's say, 100 positive examples and 4,900 negative examples. In real data, this happened very often, especially one example, like if we build a system that analyzes banking transactions for fraud, and we collect data among 10 million requests, banking transactions, we can get 500 fraud transactions, for example. And the balance is very, very bad here. So we have very skewed data. And in this situation, if we split 10%, we really risk to get too few positive examples for evaluation. And this is still the problem. So many situations when just one split doesn't work. So instead of that, if you try professional software, for example, what Tata Robot and their web interface have or any data-driven machine learning company. They apply cross-validation thing and many different approaches for data splitting. So usually we have entire data set, and instead of splitting this data set in this portion, and this portion, we can use several options how we split data. We can split also data maybe this way, and this way. Maybe this thing is going to be like from here to here, and so on. So we can use many different splits, and it's training, testing, and evaluation set, right? Something like this. And this way we get many options of splitting the data. And when we run our evaluation, we run on for all of them and then find something average. And this saves us from some randomness that could lead us potentially to bad situation.
Or some what that leads to bad situations?
Sorry?
Sorry, it saves us from what?
From bad situations that can happen because of incorrect split, accidentally incorrect split. Yeah, so that we can rely on evaluation results more. We can have higher confidence about this evaluation. But also a big question, what size of this evaluation and testing parts we usually need? What do you think about that? Do you have any guesses?
In percentage, or
The size, like, okay, we have entire data set.
in percentage, which
I can, for example, put here 10% and 10%. Is it always like this? Or maybe some different numbers? Just try to guess. If you open any machine learning book, especially classic one, this is the thing it recommends.
Yeah.
But it's not absolute truth, especially in modern world. The thing is that these numbers, they come from ages when we didn't have much data. We had, let's say, 1,000 training examples. And if we took smaller percent, like less than 10%, we would get less than 100 examples. And the risk of not, for this slice to not be representative was high. But if we have 10 million examples, 10% is definitely too much, because even to run on top 1 million examples, our evaluation process would take very long time. And it is obvious that even 10 times smaller slice will be almost no less informative about distribution things and descriptive about nature of data. So in modern world, when we have deep learning and much more, much bigger training sets, we usually don't need as large as 10% evaluation and testing set. And it's true, if you have 10 million images, you can pick maybe 1,000 for evaluation test, 1,000 for training set, and it is for sure will be enough for evaluating things. Not for sure, but it's a good guess. Maybe dependent on classes number. If we have like 5 classes, it's okay to have like 1,000 examples for evaluation. But sometimes we train system where we have 500 classes. And in this situation, 1,000 is too small for the slice. So the choice should be smart, but still we shouldn't rely just on 10%, because 10% from 10 million is too big number.
What's a good size number then?
Actually, it's kind of statistical things. You should there is a formal approach how to select such a slice to have confidence of a such level. There are several approaches for this scientific, but primarily you can use your intuition about that. So if we have just 2 classes and balanced input, it's obvious that there's no reason to have more than 1,000 examples in our evaluation set, because we have 500 of one class, 500 on another class, and that's it. But if we have 500 classes there, it is very likely that for some classes we won't get positive or negative examples. I mean, if we have to be able to classify 500 different species of animals, it is likely that among 1,000 we won't see any kangaroo, because we have too many different options. So it's this is something that should be smartly chosen by data scientists. Yes. When you have all your evaluation splits, you know how you are going to use cross-validation and split validation and training data, you can establish a working pipeline, working cycle for your project. And usually it looks like the initial phase is to try a very first hypothesis about how you're going to solve the problem. For example, you can compare this action to our very first neural network from yesterday's example. Very first one, which we trained for 9 epochs. We just check, can convolutional neural network find some principles inside data, recognize the nature of different examples to be able to split them into different classes. If we see some result, some positive result, something that is different from better than random predictor, we can say for sure, okay, data can be split, maybe we can do better. Then we pick up like some number of different architectures we want to check our hypothesis on. And for each architecture, we also can find different parameters, different options that we can try. For example, if we use VGG16, we still can try different resolutions, different color depth, maybe different number of channels. Maybe there's no need to use a colorful image. Maybe it's not to have grayscale for our situation. It's not clear initially. So we need to check all the hypotheses, and what we do next is establish our experiment plan. And it can be like, we want to try CNN with architecture 1, CNN with architecture 2, maybe VGG 16, 32, maybe another architecture. We know many neural network architectures from the state of the art, but for each of them, we also have several options with which parameters we can run this model. So for this thing, it could be this, or this line with different hyperparameters value. This is 1, 2, 3, 4. So different sets of hyperparameters. In fact, when you plan your experiment, you build such a grid of potential models and options for our experiment. And then we can just run through all of them each time when we check a hypothesis. We put here check on our ops box and record evaluation result. Each evaluation result refers to cross-validation procedure we discussed before. So we have many evaluation results for all the experiments, and we pick finally the best one. So let's say this option was the best. So we searched through the grid and found the best model. This procedure is called grid search. It is obvious that it is like a very resource demanding thing. So having this plan smaller in smart way is better because we save computational cost and time. But when we have this model, one or maybe a couple of candidates, maybe this one and this one, right? We for future rid of everything else, and then we take several candidates for model for the future. And what's happening next is we are working further with development of the system as a software wrapper for it, but also we can continuously keep improving models. So on daily or weekly basis, we can get fed updated data to both models, or maybe 3 or 5 models, or how many we have among candidates, and train them again. This can be a nice thing to do because, first of all, we can get better data. We can have continuous labeling process, or maybe we have user feedbacks and extend our training set. So we usually can rely on this process and of labeling like on something that will continuously improve our solution. So we retrain model on daily basis, and each time when we retrain the model, we compare evaluation results to what we had before, like a day ago or a week ago. And if evaluation result is better, we can put this model to production or to release candidate. And one important thing about this evaluation result is not like accuracy, but also time for prediction. Inference time. Sometimes we get better predictive power from the model, but worse running time. And we should find a trade-off, some kind of balance between. So this is how the process of finding the best model and then continuous improvement usually implemented.
Is this because just it's a new area? I mean, presumably there's some understanding of like what best practices are and.
It is a combination of like, you know, some analytically proved things, but also you have something that nobody knows about. Maybe you know nothing about this data, or this architecture brings something new to our data that we don't understand, because understanding is always the thing that cannot cover everything, right?
So people are still being surprised.
Yeah, it's true. So even in my practice, some models surprisingly performed well for situations that I didn't expect this type of model to work well. It happened many times, and opposite.
And new models are constantly being developed. Like, how old are these models?
Actually, I have nice resource for you. I will share the link with you. It is a good collection of current state-of-the-art models and the history of the state-of-the-art. And you can see there how often state-of-the-art models are updated. And believe me, they are updated very often. At least very mainstream models, they don't live usually more than 1 year, and sometimes then even 3 months. So Google BERT library that was developed in 2018 completely disappeared in its original form during 2019 because many better models appeared in the market. We still use Google BERT, but in advanced version of it. New model, it is larger, it is better, it is more accurate, and so on. And this is a very, very hot topic. What is actually state of the art? It's been updated all the time. Also, you can take a look at special. You might know Kaggle platform. Did you hear?
Oh yeah.
This is not the only one, but the most famous one. In addition to competitions the platform provides, they also have extremely nice collection of professional and amateur solutions there for many situations, and they have their own rating of state-of-the-art models, and it is updated very often too. For anything, for computer vision, natural language processing, audio processing, signal processing, weather forecast, and market forecast, and many more. Currently, entire world is concentrated on virus
prediction
things, and already they have many achievements. You can check out two resources they called like med archive and bioarchive orgs, two resources. I will share these links. And this couple of resources shares many scientific articles with real achievements in machine learning about learning viruses. Even now, it is interesting fact that NVIDIA has developed special software that allows people to run this program on their PCs. And if you run it on PC with a nice GPU, this program allocates resources of your GPU, connects to the cloud of to computational cloud that directs millions of instances of this program. And this is maybe a server somewhere at Amazon infrastructure, but maybe in some other cloud. And this distributed system is used in order to find corresponding treatment for current problem. Yeah. And they find different models, different ways how to fight the situation. And you can see many scientific articles on top of that now. They are already available and they appear every day.
May I ask also a question regarding evaluation? So here we looked, let's say, until we deploy the model, yeah? But when we deploy the model, yeah, it starts, let's say, in use, yeah? And I see here's a problem that in principle, in comparison with human being, let's say we like continuous learning, yeah, objects, yeah. But here, the problem that let's say this model could be outdated, yeah. For example, everybody start using the mask, whatever, yeah, and then only human decides that we need to update. Model, but not it's done, let's say, continuously learning with data. Is something in this direction is going on?
Actually, it's not like that. Partially, I already mentioned that, but I will add a couple of words here. First of all, if we have data-driven software, we usually collect more data all the time, right? And sometimes we retrain the model and compare the quality of this model with already deployed one. If the quality of newly trained model is better than deployed one, we redeploy better model so that we can get a continuous update of model and keep this model up to date. And this is the thing that usually for well-organized projects is done automatically. When for software engineering, it is common practice, like when you write the code, and this code is already kind of tested, you're sure about its quality as a developer, you commit this code into master branch in your repository, and this action triggers upcoming automatic action. The robot software, some automation program, takes your code, builds it, run many different software tests. We call them unit tests, integrational tests, and checks correctness for all the tests. But also, in addition to that, the system runs always testing procedure on top retrained models and compares evaluation results to previously developed versions. And if evaluation results are worse, it means that system won't be accepting these changes to the code base or to the model or to the data set because we get worse result that we had before. It's the same comparison like if we have some tests in about software failed, we also can have some tests about AI failed, and this should be fixed before rolled out for production. So it is usually launched even inside unit testing infrastructure. For that, we use continuous integration systems, but they should be aware of some specific for data-driven projects, because there is such a specific, like maybe the size of data, the size of model, something like this. Any questions?
Do you have, so for to retrain a model, is it, are you starting from the beginning? Or can you add data to a data set? Can you continue to train, or must you always kind of start again from the beginning?
Actually, there is like kind of restricted set of machine learning models that support the thing called online learning, so that we can just add to model one example and model is already improved. There is the set of algorithms that mathematically allows this. Usually this is not about neural networks, to be honest, like many other algorithms support. For example, NaivePy's algorithm, classifier algorithm supports this. But deep learning usually implies that we need to run at least a couple of epochs of training on top of that. But is still something that should be done in smart way. So maybe we don't need to retrain all this model from scratch. Maybe we can do the procedure called fine-tuning. This is also about, yesterday we mentioned that we can get a pre-trained model, pre-trained weights, load them into the system, and then continue a training process. Usually this pre-trained model is done by some big player, Google, Amazon, IBM. They have huge data and extremely powerful data centers. They pre-trained the model on medium amount of data, but we have usually slower PCs, less data, but we can use this less data and slower PC just to run at least a couple of epochs to fine-tune the model. This is actually official term. It is called fine-tuning. So we get our very specific data. Well, for example, we have big model from Amazon that can, let's say from Facebook. They have FISS library with well-trained model for face recognition. But also we can have our own smaller data set with faces. For example, from Japanese market, Asian type of face, it is different, and general model, common model, can perform not ideally on Japanese faces. But if we have some data set with Japanese faces, we can use general model to fine-tune this model to be more familiar with Asian type of appearance. And this small fine-tuning process makes the model much better. And yeah, so every time we get new slice of the data by annotating or maybe collecting during user feedback or something, we can use small portions of data to try to fine-tune the system and to see if it performs better or not by running evaluation.
So retraining, almost kind of by definition, means starting from the beginning, and if otherwise, it's called fine tuning.
Fine-tuning, yeah, yeah. It's you know, this fine-tuning is you can also have pre-trained model and run some retraining on this weights, and this can be not a fine-tuning if you run many epochs and retrain to very different domain, for example, because if you are working with animals, but you are switching to, let's say, medical things like X-ray shots of organs or something, these couple of domains, they're very different. So pre-training provides something for your case, but not a lot. So you still need to train quite kind of long process. And this, technically, we can call this fine-tuning, but in fact, this is retraining. So fine-tuning is something that it's like with radio. You can tune and you can fine tune. So fine means like very accurate small movements, not big changes. And this is the answer. Like if you update values slightly to be more accurate for very specific slice of data of this type, it is fine tuning. If you retrain something, it is also training. But there is another thing here. About fine-tuning and retraining, important thing is that also sometimes we need to solve different things. For example, we have well-designed model that can distinguish genders of people. So we have neural network with many layers that has an output item, and here we have some kind of sigmoid function that can say whether it is a male or female. But we want to use this pre-trained things in order to understand, let's say, age, or to be able to recognize nationality. Many features, many face features, maybe some clothes features are descriptive enough to rely on, to be able to distinguish Japanese people from Moroccan people, from maybe African people, and from, let's say, Russian people, Caucasian race. To be honest, in some countries it's illegal to run this type of detection and use this in production, but technically this is possible. And the thing is that this model, you can remember that many convolutional layers here, they supposed to be something that extract important features of faces, right? We use in the model when we detect gender, we get all these features and use these features to predict gender. But also, almost the same set of features can be used for race prediction, or maybe prediction about age. So that potentially we can load all the weights for all these layers here, or for some of them, maybe like this portion, right? And then remove some layers here and substitute them with another part. Let's say, let's put here softmax output with four different outputs, and each output will be initialized when we have corresponding race, or maybe age range, and run the training process. And all these weights that we have already downloaded and deployed into our model, they can be helpful much better than randomly initialized ones. So this technique, when we change one or two or several output layers and retrain the model for new type of data or new type of output. It can be still classification, but maybe multi-class classification or even regression like gender prediction. So this technique is very, very widely used. People use this in many, many projects. And this is the way you can build something new for space related predictions. Maybe you want to predict the moment when a person lies. Do you remember this series, Lie to Me? There is some series about the name Lie to Me, and it is about a special expert who is able to see when the person lies just by some features on the face. So we can potentially develop the system that will be guessing with some accuracy when people have some emotions and thoughts, maybe small changes on the face that show that maybe the person is lying, something like that. Yeah. So this is also type of fine tuning, but it also implies changing the architecture, changing output layers. And during the training process, it's not always like we retrain, correct all the weights inside. Sometimes we can have several layers that we don't want to update. And during the training process, we can freeze some layers, and they are not going to be updated during the training process. So we will train just the slice of our layers. Yes. Okay. So this is about fine-tuning evaluation, and it should be also the answer for the question about online learning. For neural networks, we usually retrain the model by schedule, and if a new version of model performs better, we can redeploy the model. If not, no need to redeploy. Okay. All these things should be integrated with continuous integration systems. They call CI or even CI/CD, continuous integration and continuous deployment. Even GitHub and many open platforms, and for sure each commercial platform, they have a solution for continuous integration and continuous deployment. So when you add some data and some changes to the code, system pulls this, retrain it automatically, evaluate automatically, and shows if any errors, some alerts to developers, But if everything is okay and evaluation went well, it also can redeploy solution automatically. And many companies use this. So when they want to redeploy a new version, they usually put some special Git tag in their Git repo. System sees this Git tag, and this is the signal to be redeployed, for example, automatically. The next thing.
And in your company, do you use your own infrastructure or you use some cloud services?
Usually, for our case, like for AILabs.org, we have many customers, and for each customer, it is usually slightly different. Some people have infrastructure in GitHub, some in Bitbucket. Other companies can have their own Git repos. So it is kind of diversity of options. So each situation can require some specific thing. But yes, we try to reach this point where we have continuous integration, continuous deployment, and continuous evaluation. But to be honest, in many projects, it is done manually because like rolling out of such a powerful automation makes sense only if we have large long-term projects. If it is a question of experimenting for several months and rolling out the product, it means that we might not have enough resource, or even if we have this resource, there's no real need to do this because this continuous part won't be going for years. For companies like Grammarly or DataRobot or Amazon or Facebook, who improve their models for years, they need such thing for sure. Continuous integration, continuous deployment, and they do have. Actually, fortunately, had a chance to see how this happening in Grammarly infrastructure and DataRobot and in Facebook too. So it's interesting observations, and to be honest, sometimes I was kind of surprised that they have lack of automation, but soon they got this automated. So yeah, it's very popular approach. About models deployment and what you actually can try. Many of you guys might work on Windows and Mac OS, and much more rarely you use Linux as your desktop operational system. Most of models are designed to be deployed on Linux machines, primarily. Like I'd say 90% of AI world lives in Linux infrastructure. It is still possible to deploy something on Windows machines natively or using Docker. Docker is a very powerful thing that currently can be rolled out on Windows machine because of virtualization layer there. But you can also try some models in collab infrastructure or in cloud infrastructure also. You can rent a machine in Amazon in EC2 service and get this instance with Linux and roll out the model there by hands or using Docker. But also for very basic predictions, There are some existing solutions in clouds. For example, you can try, actually you will try during this course, you will try the model on Microsoft Azure. There is a face recognition model there, and you can check some functionality there. And you will be able to do this a little bit later. Tomorrow we have almost entire day dedicated for different experiments. And one of the tasks that you will have is will be to try Amazon, not Amazon, Azure based solution. But Amazon, IBM, and some other company provide their own solutions for face recognition, and not only. Each big cloud vendor like Amazon or Microsoft, they already have some cloud-based machine learning solutions with pre-trained models there. It's not only face things, it's like gesture detection, object recognition, object segmentation, many pre-trained models that can detect common objects of maybe 500 classes, like people, birds, and different animals, vehicles of different types, maybe trees, houses, windows, doors, car plates, and so on. Many different. And for many solutions where you need some AI inside, you can find maybe already existing model. If you need to be able, for example, to detect if this is the photo of the same person or not, you can develop your own model or download someone's implementation and deploy on your server. But also you have an option to use publicly available model on Azure or Amazon. They have such an API to compare one photo to another photo, or one photo to set of photos to check if it is the same person or not. They also provide age, gender detection functionality, and some other things. Orientation. Face can be like this, so angle detection. Different models work better or worse with different camera positions. Amazon and Azure, they already have some models that detect face angle. I mean, in relation to camera and so on. So you will see this a little bit later in example. Okay. So please give me 5 minutes break, and I'll be back. This is an example implementation for Azure client. So
can you repost the link to the document?
you don't see it there?
Where is it?
It is already there. I just navigated it. I posted it again, but this is the copy. You should be able to see two same.
No, I mean a link to the Google document, to the main doc.
Oh.
A link to the doc where all the links are.
Yeah, just a minute.
Yeah, thanks. I closed the window and now I don't.
Yeah, I understand.
Thank you.
What shall we do? Just to look at it? Or...
First of all, I want you to make a copy of this notebook to your drive. So file save to drive. And then you can run it. I want you to run it now. Here you see the example on how to use cloud services provided by Microsoft about face recognition features. They have special service with endpoint. The name is cognitive service azure.com. And this is the entry point for Face API. They have many functions for face features detection. And if you go through the code, it is quite simple one. You'll see all the operations you need to do to detect something for your face, including age, gender, and the ability to compare two photos to understand is this the same person or not. Here in document you have examples of all the calls. Of course, there are much more detailed explanations about how to use this. There is an official API description for this service. The same thing is existing for Amazon.com and others, and this is just a working template. Do you hear that? Sorry, my neighbors. What is important here is that you might see the block with key and endpoint description. And this key is something that should be provided for people and companies individually. So this is a test one. So you cannot run too many predictions on this key. You cannot build a product that uses this key, but you can test how an API works with it. So if you want to build any product with face predictive model, you can acquire new key, your personal one, and for some number of requests a day, this is for free. But if you load the system a lot, it is like they have different plans, paid plans. It's one of the options how you can work with faces. One important thing about face is that even photos I used here are not good enough for some face recognition tasks, because what they expect is like passport-like quality of photo. But sometimes you can use or fine-tune models for special things. For example, in shopping mall, we see people faces with security cameras, and we detect age and gender. Actually, one of the difference between restrictions in San Francisco and Tokyo that we talked about during the meeting with Hiroshi is that in Japan it is still allowed to take pictures of people. It is still allowed to detect age, gender, and many other features. And it is still possible to even save the photo on the same server. The only thing you cannot do is run any person identification code. In Europe, even this is not available, because you cannot save photo on hard drive at all. But even things like, if you get age, gender, time, and color of clothes, they potentially can consider this information to be sufficient for detecting who this person was. And even having some data that potentially can be used for guessing about exact person is illegal in Europe. In Japan, it is legal to store this data. You cannot call the code that does this identification. And this is a big difference, because in Japanese solutions, we can still store data and even collect data for further model improvement. We can record some movements of people in shopping mall, get these videos here on Ukrainian side, and run data annotation process, like select bounding boxes for people, then retrain and fine tune our model and reuse this model. For European reality, it's forbidden. For California, it's forbidden. For US, it is still available, but not for all states. In Canada, it seems to be possible, but with some regulation too. So, did you have a chance to run this document? Is it
Yep.
working?
Seems to be. Yeah.
So, this is a web-based version. So to get images here, I had to find links to direct links to photos. So if you have any photos of yours, you can just substitute URLs here and check on your photos. They should be navigable by link. And what you can do here already, you can build a simple Python script that detects whether the person on photo this person or not. It works in a way like you upload the photo to detect some features, and this photo is stored in cloud infrastructure for 24 hours. During this period, you can access information about this photo and mention this photo in other calls by specifying photos ID. So that if you uploaded one photo to infrastructure, to cloud infrastructure, you can easily use any new photo and compare it to previously uploaded by specifying an ID. You can learn the code below, and you will see how it is done. Yeah. At the bottom, you can see like 1, 2, 3, 4 photos, 3 of me, and another one is Hisato Kashine, my colleague from Japan. And I compare photos to be me or not me here. And the last couple of blocks is comparison me and me and Hisato. And you see the decision, the same person or different people by comparing with decision boundary. It is done internally in cloud infrastructure using their models. Alternatively, you can download existing models and deploy on your laptop somewhere. And actually, even if you use Windows, you can try that. But if you use Windows, you will need to use Docker or virtualization for that. Yeah. Most predictive models work better and faster on GPUs, but almost like 95% of models can still use CPU for prediction. It takes just more time to get the result. For prediction for one photo, you won't feel any big difference because for human being, it doesn't matter whether it is it takes maybe 20 milliseconds or 1 second. For you, you won't see the real difference. But for production, for application, it is very important how quickly API or solution and returns the answer. And if you have lags there, no problem. Just a moment. API can be different for different clouds, or should I say maybe it is different for different clouds. But the simplicity or complexity of its usage will be almost the same for any cloud. Here you can see 4 types of problems we solve. The first one is face detection. We recognize the region where the face detected. So it is an object detection thing, and we already mentioned that object detection means detecting whether the thing is on the picture and proposing the region on the picture where the object is located.
Are you? Can you share your screen?
Yeah, for sure.
Or might as well.
Yeah. So here you see like object detection for face. You should when you talk to customers or data scientists, it's better to follow proper terminology. And when we say face detection, it means that we perform object detection for faces. Object detection means finding this bounding box about location of an object on the photo. Another task is age detection and also gender detection. Actually, this line, oh, sorry. Sorry. What type of attribute we want to draw on the picture? Face attributes is a data structure, an object that is returned by API. Sorry, neighbors making some noise. I will put on pause for several seconds. So Jupyter notebooks allow to get like some help when you press Control Space. So here you can see different attributes. Emotion. As I understand, this is about bird. This is gender, if I wear glasses or not, and blah, blah, blah. It's interesting to try different attributes, and I'd recommend you to do this now before we go further. It's interesting, actually. Occlusion, noise, gender. It's interesting what type of gender system will show for me. Sometimes it makes mistakes. No, so I need to rerun entire.
Glasses.
Of course, if you have some error in prediction, it's okay, because in order to have nice prediction, you have to provide a nice quality of image, and still there is no such a thing as 100%. Okay. So then I print face attributes. It's a dictionary. It says that I'm not smiling, but it's not true. And that I don't have facial here. It's not like this. Not wearing glasses. Emotion none. Hair none. Makeup none. Occlusion none. Accessories none. So this is very dependent on image quality. Just try something alternative. You can do this. Let me check. Let's take some face with emotion. Well, it's AI actually. I will be talking about generating of pictures. This is AI generated photos, not real people. Okay, let me check. Face with emotion. Okay. Okay, let's take this one. Not best. Okay, it takes time. I don't want to spend much time on this. Well, maybe this will work well. Let's copy URL. Actually, it's interesting because the set of attributes that API returns is different. So,
but you did that just detected faces. The attributes is later. You need to run the next block.
Sorry?
You need to run the next block.
Yeah, sure.
That's
yeah,
the attribute block.
Yeah, I understand. Yeah, you're right.
There we go.
Yeah, you're
Smile
right.
none. Yeah, so that's not very good.
So it is still not showing the effect of smiling. This emotion here. So you can try this a lot. What you can also do, you can use your local photos, not only specifying them by URLs. It's a little bit different call, but let me provide you with a link with examples how to do this from for local photos. If you want just an example, this is not launchable, but it is something that just a moment. Something that can be used for example for trying this. Okay. There's also the link in the document. You can check this link. It is very similar to what you see here, but the difference is about loading pictures not from the internet, but from the local folder instead. It will help you if you want to try on your local photos. Actually, this is a real situation from a shopping mall. This was an experiment about whether we can detect faces from security cameras or not. And actually, the answer was not for this model. Okay. This is the thing I wanted to show. Let's say we have dog, cat, cat, dog, 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 cat in data set. And we have ground truth. We know that dogs are zeros, cats are ones. 1, 2, 3, 4, 5, 6, 7, let's say 8. But our model predicted something that is slightly different. Not slightly. And for this situation, we can draw such a thing that called confusion matrix. This line is supposed to be dogs, this line cats. This is also dogs, this is cats. And we can count all the dogs that were detected as dog and put the number here. Like this is 1, this is 2, this is 3, right? So we put number 3 here. We want to put all dogs that detected as cats here. So this is the no 1, 2 cases, right? Also, we want to put all the cats detected as cats here with 1, 2. So this is 2. And here we want to have all the cats detected as dogs. So we have just one situation like this, right? So this is confusion matrix. It characterizes a classifier and says how often and in which situations system confuse more. Ideal version of this would be we have 1, 2, 3, 4, 5 dogs and 1, 2, 3 cats. Ideally, we might have here like 5 dogs, 3 cats, 0, 0, right? In fact, we have something different. So ideal confusion matrix has very high numbers at main diagonal and very low numbers here, like zeros. In real life, this happens very rarely, and even if so, it means maybe we already have some problems like overfitting or something. This is for 2 classes, but if we have many classes, we still can build confusion matrix. And this confusion matrix can be used for generating, for computing several different metrics about quality. First of all, can we make a conclusion about accuracy using this matrix? What do you think?
Yes, true positive divided by total number of.
Generally, we take main diagonal, sum of main diagonal here, and divide by all the number of items. Also, we can use this matrix for understanding what which value for precision, recall, F1 measure, and many other metrics just on top of this matrix. Yeah. And this is the thing you can really show to the customer when you are trying to show the results, because accuracy itself isn't something very descriptive. But if you have a picture like this, actually what you see here is confusion metrics for Azure outperforms on photos from shopping mall when the text detects age range for a person. So we have 6 different ranges from 0 to 10, from 10 to 20, and so. And system detects with this confusion. So you see that we make mistakes pretty often. But generally, there is a nice correlation about between density and a main diagonal. This means that the system works kind of better than random one, even much better than random one, but still can be improved. And for this situation, I think the improvement shouldn't be for model itself. It should be for the way how we get photos. Because for each task we solve, we need to provide data of a type of the system was trained for. If we take image of face, like photo of face in bad light conditions and under different angle, different resolution. It means that model can perform worse or even cannot work at all. So one of the things we will be doing tomorrow is performing some experiments with cloud model, but also I will ask you to try to deploy model locally or in Google Colab, and we'll be discussing this with you during entire tomorrow. Today we also have some theoretical things to discuss, and also we didn't mention generative adversarial networks that are actually a very state-of-the-art things, so we should mention that. For now, I think we can have lunch break or something, and be back like maybe at 3 p.m. if you want. Guys, I have a question. Did you have a chance yesterday to run this fine-tuning Jupyter notebook?
I ran it, but I didn't look at the results. Let me
Did
see.
you use GPU acceleration for that?
Let's see, do I have it open still? No, runtime disconnected. No.
So you might didn't turn on this option about GPU.
Where's this?
Let me show you again. Here, change runtime type. You should have selected GPU.
Where was that? Where? Under
Just
what? Under
GPU.
runtime?
Yeah, it's like runtime, change runtime type, GPU.
GPU.
Is it selected or not?
Yeah, it was selected. Yeah.
So you can just relaunch it. I really recommend you to try these networks with different parameters. Maybe what you can change here is, let's say, not this one. Sorry. What you can do here, first of all, you can experiment with a number of epochs, but also you can try several options for a number of layers here. You can easily add, for example, one additional convolutional layer. It will make neural network work much longer, but still can be some improvement in quality. Or it can make the model worse. Just experiment like this, adding different convolutional layers. Also, it's a nice idea to remove dropout at all to see what will happen, and to change with several different dropouts. You can use the dropout here, and actually you can extend number of layers. I mean regular layers, dense layers. So you can do like this, something like this, and try to train the model again. This way,
And then what are we comparing after we train the model? So what things are we looking for to compare?
you can initially you should run this Jupyter notebook as it is without changes. It should be completed, and just write down the output accuracy and maybe loss function value. Then you can add some layers, but please, when you run this, you probably can put a little bit more epochs here. The reason is that way you will be able to see the moment when the overfitting comes. I want you to let's check overfitting for very first example. Oh, it's not that notebook I launched yesterday. Is there anyone using Linux on the laptop?
No, not me.
It happened so that I switched like many years ago. For now, I even not sure what is possible to do with Windows now, because forgot how properly work with it. Long time ago, I used to be a software engineer for Windows platform, but now it is so.
For some reason, it's not letting me.
Yeah, I forgot.
Sorry,
what? So, this. So here I put 25 epochs instead. Let's wait while it goes through.
It won't let me mount the data for some reason.
Sorry?
It won't let me mount the data for some reason.
Just a moment.
Yeah, I got the authorization code and all that kind of stuff, but it doesn't, for some reason today, it doesn't want to.
You can avoid running it now. We see the screen, so yeah, you can do this like later on. This authentication is just needed to get access to your Google Drive to download data from Google Drive. For now, you can also see that we get a validation accuracy lower than before. This means that we already overfitted by this point.
Cannot access.
It's like plateau. We cannot reach better result at this parameter of neural network.